Hello, welcome. You're with Bahati Abdul Karim, and I'm taking you through A-level applied mathematics. As I told you, we are still on projectiles, and this part is suitable for students who are doing mathematics at A-level, Senior 5 and Senior 6. Let's look at what we're going to learn today. So for today, we're going to look at projection at an angle. As you remember, in the last video, we looked at the definition of a projectile and horizontal projection. So today, we're going to look at projection at an angle. So for projection at an angle, the velocity of a particle launched with a velocity u. This is the initial velocity of the particle that we are going to launch, and at an angle theta. As you see, the velocity u will be at an angle theta to the horizontal, and this velocity u can be split into the horizontal and the vertical components, as we are going to see. So what you see here is a particle released from this point up to this point, and it was given an initial velocity u and at an angle theta. So this distance here you see is the range, and it is the distance from the point of projection to the point when the particle lands. Then this distance here is called maximum height, and this distance is at a point when the maximum velocity, or the final velocity in the y direction is 0. At this point, the final velocity in the y will be 0. Whenever you throw a particle upwards, the force of gravity acts on it, and it reduces its velocity until that velocity becomes 0. And then at that point, the particle starts moving back to the ground. So this displacement will always be the maximum height. So let's get back to our initial velocity u. So whenever you launch a particle with the initial velocity u at an angle theta, you have to resolve this velocity u to the horizontal to get its component, and it will become u cos of theta. And you can resolve it to the y direction to get u sine of theta, and that will be its component in the y direction. So this is what you will get. When you resolve this u to the x, you will get u cos of theta. When you resolve it to the y, you get u sine of theta. So you'll have to always remember that when we're dealing with horizontal projection, you remember we did not have u in the vertical direction or in the y direction. So here you'll have to have u in the horizontal and in the vertical directions, and here I summarized it. So at time t is equal to 0, when t is equal to 0 at this point here, then you'll have horizontally your u in the x will be u cos of theta, and the u in the y will be u sine of theta. Let me hope this is clear to you. So let's now see how we can get velocity at any time t along the way when the particle is still in the air. So we are going to do this using the first equation of motion. So as I told you, we use the 3 equations of motion, and in here to calculate velocity at any time t, we are using the first equation of motion. I'm going to start with the y direction. So for the y direction, let me get a pen. For the y direction, we know that velocity in the y can be got. So that is what we're going to get, and we know that u in the y is u sine of theta. And then we know that acceleration in the y is g, but it is a negative since the particle is moving upwards opposing gravity. Then we know that time can be taken as time t. So using this, we can get velocity in the y, and if we substitute these in this equation, we shall get v in the y equaling to u sine of theta, and then minus g t. And that's the equation that you can always use to get velocity in the y at any time t. If I want to get the velocity in the x at any time t, remember here we are considering vertical motion. So here for the x we are going to consider the horizontal motion. Let me write it. For the x direction, we know that we are considering now horizontal motion. And in here, we know that v in the x can put a question mark. We know that u in the x will be u cos of theta. And we know that time can be taken as time t. So in that case, if I substitute in the same first equation of motion, I will have v in the x equaling to u. Our u is u cos of theta, and then actually I forgot the acceleration. Acceleration in the x will always equal to 0. So we say plus 0 times t. So v in the x will always be equal to u cos of theta. And that's the equation you'll always use to calculate velocity at any time t in the x direction. So let me hope this is clear to everyone. I had summarized this information on this slide. I think we can go through it. Let me first erase this. So you realize that horizontally our v in the x is u cos of theta. I think I've derived that, and vertically our v in the y will be u sine of theta minus gt. I think we have also derived that. The horizontal component of velocity is constant throughout since there is no force acting in that direction. I think that one is also clear. And then the vertical component of velocity changes continuously because of the weight of the particle acting downwards. And then at time t, the displacement of the particle can be found using s is equal to ut plus a half. This is a half at squared in the horizontal and vertical directions. And when you try to substitute the vertical the information for the vertical direction into this equation, you will end up getting ux equal to ut cos of theta, and then vertically you will get y equal to ut sine of theta. I'm going to show you how these two are got. We know that if we are substituting the information for x in this equation, we will have s in the x. We can say s in the x, we are considering horizontal motion. S in the x will be equal to x, let's call it x, and then u in the x can be u cos of theta, and then we know that t can be taken as t, and then we know that acceleration in the x will always equal to 0. So if you substitute this information into the second equation of motion, you will have our s is x equal to u. Our u is u cos of theta, and then times t, then the rest will be a 0 because acceleration is 0. So you now come up with what is here. And then if you want this one, you will have to substitute the information for y. You know that the displacement in the y can be taken as y, and then maybe let me first run here so that I can use this space. So for y we know that, let me summarize that information, s in the y will be y, and then we know that u in the y will be u sine of theta, and then we know t can be t, we know that acceleration can be g. So if you substitute this information into the second equation of motion, you will have y equal to u, which is u sine of theta times t, then minus a half g t squared. So you realize that this is this equation. So that is how simple it is. So whenever they ask you to determine or to calculate any displacement in the x or in the y, you can still use these equations. So let's see what is next. Next, we have maximum height, range, and time of flight. So suppose a particle is initially launched from O with an initial velocity u and at an angle theta to the horizontal, and then there are three main things that can be calculated. 1, the maximum height, and then 2, the range of the flight, and then 3, the total time that the particle is in flight. So we're going to see how we can calculate all these three things, and these are some of the common things in projectiles when it comes to projection at an angle. So here, let's start with maximum height. I'm going to derive the equations that you can always use to calculate maximum height, range, and time of flight. The way I derive them is always the way I always want my students to know how they are derived. Because if you cram them, sometimes you can forget something and you end up failing the whole question. It is always better you understand where they come from. So I'm going to derive the equation for maximum height, but you should know how we come to that equation, because if you cram it, you may make a mistake. We derive also for range and time, and also I want you to know how it comes about. So let's go and see how we can derive the equation for maximum height. So as we know that if our particle, let's say this is the y direction, this is the x, you may project your particle from here, it comes up to there, you may give it some initial velocity u, and then this may be the angle of projection. So we know that the maximum height will be that distance, let me call it h, and one characteristic we know about that point is that v in the y will always equal to 0. So if you remember that, you're good to go. So with this diagram, I can now derive the equation for maximum height. I know that maximum height will be the displacement in the y. So my displacement, considering vertical motion, my displacement in the y will be h. I know that my u in the y will be u sine of theta. I know that my v at that point will be 0 where I have h, and I know that time can be taken as t, and acceleration will be g, but negative. So with this information, I can derive the equation that we can always use to calculate maximum height, and we're using nothing else apart from the three equations of motion. So you think first, which equation do you think we're going to use for this distance h or displacement h? I think you can see that we can use the third equation of motion. It can work properly, and also the second equation of motion can also work properly. So using the third equation of motion will be the easiest, but when we say we are using the second equation of motion, that means we just need this time taken to reach this point for us to be fine. So let's see, if we are using the third equation of motion, we know that the third equation of motion will be v is equal to, actually v squared is equal to u squared plus 2as, and if I substitute, my v will be 0 squared equal to u is u, and we have sine of theta, and this whole thing is squared, minus 2g, and our s is h, which we are looking for. So you realize that here, if I take this part, this side, I will have 2gh equal to u sine of theta squared, and u is also squared. If I divide by 2g, I will have my h, which is the maximum height, equal to u squared sine squared theta out of 2g. So this equation, you can always use it to calculate maximum height. So I hope it is clear to everyone. And then after that one, you can still use the second equation of motion if you want to, and the first equation, you will still get the same answer. If it fails, you can write to me through the comment section. I will have to give you a reply. So let's now see how we can derive the equation we can use for the time of flight. So we can use two alternatives for time of flight. We know that the time the particle takes to move from here up to here can be multiplied by 2 to get the total time for the whole flight. So if we can get the time from here up to here, we just need to multiply it by 2, and that's all. And another thing that we can use, we may decide to use vertical displacement, because we know that at this point and at this point y is equal to 0, that is s in the y is equal to 0. So we can use that one also to derive the equation we can use to calculate the time of flight. Let's do that. Let me first erase this information from this slide. So let me redraw this diagram. So let me hope this is our particle. We know that this is y, this is x. So for time of flight, I'm going to use vertical displacement, and this particle was given u, that is the theta, and the time of flight will be the time at that point, and at that point t, we shall call it capital T. So considering vertical motion, I have u in the y equal to u sine of theta. I have v at this point, we do not know it, v in the y at that point, we do not know it, but still we don't need it in this case. And then time will now equal to capital T, then acceleration will be negative g, and then lastly s in the y will be 0 at this point and at this point. Since we are interested in the time of flight, at this point will be 0. So if we use that, we'll have to substitute this information into the second equation of motion, which is s is equal to t plus a half a t squared. So we substitute here, and we'll get s in the y, which is 0, equal to u, our u in the y is u sine of theta, then times t, our time in this case is capital T, then minus a half g t squared. So in this case, when you reach here, you can factorize t outside. You'll have u sine of theta minus a half g t, 1t, and b outside. And if you have such an equation, then that means either t either t is equal to 0 or it is u sine of theta minus a half g t, which is equal to 0. And in this case, where is t is equal to 0? It is at this point before projection, actually at the time of projection, and this will be for this point when the particle is landing. So in here, if I make t the subject, I'm taking this side. I will have a half g t equal to u sine of theta. Then I will have to multiply by u and divide by g. I will have to multiply by 2 and divide by g. So I will have to have t equal to 2u sine of theta out of g. You can always use this equation to calculate time of flight. So for the range, we shall have, let me draw this diagram. This is y, this is x. We know that the range is this distance from here up to here. That is our range. And we know this particle was given initial velocity u at an angle theta. So if I use horizontal motion, and I'm considering motion in the horizontal direction, our s in the x will be r. Our u in the x will be u cos of theta. Our acceleration in the x will be 0. Our t in the x in this case will be up to t, because it is the time of flight from this point up to that point. And I think that's all. So if I substitute this information into the second equation of motion, I will have s in the x. The second equation of motion is s is equal to ut plus a half at squared. So s is r equal to u cos of theta, and then times capital T plus a half times 0 times capital T squared. So in this case, you realize that you'll have u cos of theta times capital T. And you remember our capital T? Our capital T was 2u sine of theta out of g. So you bring it in here. So you will have u cos of theta times 2u sine of theta out of g. So if you use trigonometry knowledge, you realize that 2 cos of theta sine of theta gives sine of 2 theta. You know that? You can say from sine of 2 theta equal to 2 sine theta cos theta. We shall have our range now equal to, now we know this u and this will be u squared, then cos 2 and sine theta, that is 2 sine cos theta sine theta will be sine of 2 theta, then we divide this by g, and that's all. So this equation here will always be used to calculate the range in the x direction. I think it is very clear to you. So here we have our question 1, and it says that a particle is projected with a velocity of 19.6 meters per second at an angle of 30 degrees to the horizontal, and then find the time taken for the particle to reach its maximum height, then b, the maximum height reached by the particle, c, the total time of flight, and then d, the horizontal range of the particle. So you can calculate all these using the 3 equations of motion, or you can still use the formula that we derived. We derived different formulas for this part, so you can use and then to calculate the time taken to reach the maximum height, and then total time of flight, and the horizontal range. So here is our particle, and given this information of u and the angle, we can calculate on this. First things first, we should always first summarize the information for a given part that we're going to answer. For example, part A, the time taken for the particle to reach the maximum height, you have to first locate that maximum height and then summarize your information. So let me sketch the diagram. This is a particle. We know this will be our maximum height, that distance here. Then we know that our particle was given an initial velocity of 19.6 meters per second, and the angle was 30 degrees. So if you want the time taken to move from here up to here, we're going to use the vertical motion. So I can say that vertically we know that u in the y will be 19.6 sine of 30 degrees. We know that acceleration in the y will be 9.8 meters per second, but it's a negative since we are opposing gravity. We know that at this point our v in the y is equal to 0, and we can call our time to be t, and then lastly we can placement s in the y will be h, which is this distance at that point. So using this information we can calculate the time taken to reach that point. So I'm going to use the first equation of motion from v is equal to u plus 8t. I know my v is 0 at that point. My u is 19.6 sine of 30 degrees, and then minus 9.8 t. So this becomes 19.6 times sine of 30. Sine of 30 is a half. You will get 9.8 minus 9.8 t. So we bring this side, we shall have 9.8 t equal to 9.8 divided by 9.8 by 9.8, and you will have your t equal to 1 second. So after answering part A of the question, we get our time as 1 second. So this time here, we can use it to answer part C of the question, which was asking for total time of flight. If this t is equal to 1 second, then the time here will be 2 seconds. It's just this time times 2. So I think part A and part B are clear. Now let's see how we can calculate maximum height. So for maximum height, I think here you are clear. Time to reach this point is 1 second, and the total time of flight will be 1 times 2, which gives you 2 seconds. So let's now calculate the maximum height using the same information for y. But using a different equation. So here we're going to use now the second equation of motion. So we can say from So here we're going to use the second equation of motion, and we can say from s is equal to ut plus a half at squared. We know that our s is h, and it's what we are looking for. and then our u is 19.6 sine of 30 degrees minus a half times 9.8 times 1 squared. So here 19.6 times a half gives you 9.8 minus 9.8 divided by 2 gives you 9.4, which will give us 4.9 meters. So this is our maximum height. And then if we want the range, we can use the same equation, but we're going to use information for the horizontal motion, not for vertical motion. So in this case, let me summarize the information for the range. But first, let me first rub this information. So since we want the range will be this distance, and it is in the x, so we can say horizontally, we will say that our s in the x will be the range that we are looking for. Our acceleration in the x will always equal to 0. U in the x, we know it is 19.6 cos of 30 degrees, and then our time taken to reach that point will be 2 seconds. This time from here up to here is the time of flight. So using this information, it is enough for us to calculate the range. So we can say from s is equal to ut plus a half at squared. We know that our s is taken as r and our u is 19.6 cos of 30 degrees. Then this whole thing times 2, which is our time. Then this time here plus a half times 0 times 2 squared, and this will give us 33.9 meters, and that's our range. So at that point we have finished the first question. Let's go to the next question. The next question says a particle is projected with a velocity of 25.48 meters per second at an angle of sine inverse 5 out of 13 to the horizontal. Find the maximum height reached by the particle, and then B, the horizontal range of the particle. So this is how our particle moved. It was given an initial velocity of 25.48 meters per second, and the angle is sine inverse of 5 out of 13. So given this as the angle, you can keep it as this. So from here, if you have your theta equal to sine inverse of 5 out of 13, you can take sine this side, you will have sine of theta equal to 5 out of 13. So if you have this, you can also get cos of theta, because you know sine of theta is opposite over hypotenuse. So in here, if you use the if you draw your triangle and put your theta maybe here, then the opposite will be 5 and the hypotenuse will be 13. If you look for the adjacent, you will find that it is 12. So in here, you can still look for cos of theta, and your cos of theta will be equal to adjacent out of hypotenuse, which will be 12 out of 13. So Here you can get sine of theta and cos of theta. I always recommend you to keep it like that. Don't get the angle in decimals. Just keep it like that for simplicity. So to find the maximum height reached by the particle, this is the distance here. So you know what we consider. We're going to consider the vertical motion, and first things first, summarize the information we have first. So for u in the y, we have it as our velocity was 25.48. We know it is 25.48, and then sine of theta, then this becomes 25.48. Sine of theta is 5 out of 13, so you can keep it like that. And then we know that the velocity in the y at maximum height is 0 meters per second. We know that the displacement s in the y at that point can be represented by h, and then the time taken, we do not know it, and then our acceleration in the y will be 9.8 meters per second squared, but it's a negative. So using this information, I can use the third equation of motion. So using the third equation of motion, which is v squared is equal to u squared plus 2as, we know that our v squared will be 0 squared equal to u, which is 25.48 times 5 out of 13 squared, then minus 2 times 9.8 h. So when you simplify this, you'll have 0.9.8 squared minus 19.6 h. When you bring this side, you'll have 19.6 h equal to 9.8 squared. You divide by 19.6 by 19.6. You'll end up with your h equal to 4.9 meters. So as simple as that one. So after calculating our maximum height reached, the next part is asking for horizontal range. So for horizontal range, we shall consider the motion in the x direction. So we can remove this and summarize the information for the horizontal direction. For the x direction, we know that our u in the x will be 25.48 cos of theta, and this will be 25.48 times 12 out of 13. We have already seen how to get cos of theta, and then we know that our displacement in the x, we can call it r in this case for this part, and then v in the x, we can put a question mark, we may not need v, and let's use time as t, the time to cover this distance, and then we know that acceleration is always equal to 0. So using this information here, we cannot get the range because we do not have time t for covering that displacement. So we have to first use the vertical motion or vertical direction, the motion in the vertical direction, to get the time of flight. After getting this time of flight, we can get the range. So I'm going to use using s is equal to ut plus a half at squared. I have already summarized the information for y, so I will not summarize it again. I know that s when the particle lands, that is, if the motion is like this, at this point and at this point y is equal to 0. So my displacement practically will be 0 at this point. If I want the total time of flight, I know this will equal to u, and u is 25.48 sine of theta, which is 5 out of 13, and then times the time of flight that we need is t, and then minus a half times 9.8 times t squared. So in this, I factorize t outside, I will have 25.48 times 5 out of 13 minus 9.8 divided by 2 will get 4.9, and we remain with 1t when we take 1t outside. So we shall have a t. When you multiply this t here, you will get back that. When you multiply it here, you will get that. And this is equal to 0. So you'll have either t is equal to 0, or you'll have this part equal to 0. And for t is equal to 0, it is at this point of projection. At this point, time t is 0, and at this point, we'll have that. And we'll have 4.9 t equal to 25.48 times 5 out of 13. When you simplify, you will get your t equal to 2 seconds. Let me hope it is clear. Then after getting time of flight, you can now calculate the range. If you want the range now, you can say the range is equal to, using the same equation, it will be horizontal component of velocity times time of flight, or you use the equation that we derived. So in this case, for me, I can just say that r is equal to horizontal component of velocity, which is u cos of theta, and then times t, because I know acceleration is 0, times the time of flight. So let me create some space, since we have already calculated our time. So we are using the same equation, and I'm not going to rub it. We have our s, which is for r equal to u, and the horizontal component of velocity is 25.48 times 12 out of 13. Then times time of flight, which is 2, then plus a half times 0 times 2 squared. So this gives us 47.04 meters as our range, the distance from the point of projection to the point when the particle lands. Let me hope this is clear to everyone. Let's go to our next question. Our next question is saying a particle is projected at a velocity of 12 meters per second at an angle of theta degrees to the horizontal. The maximum height reached by the particle is 5.3, then find theta, that is the angle of projection. So here they can twist the question in any way so that you can find the information that is not given. So as I told you, don't panic. First things first, summarize the information. In this case, if I'm given maximum height, I know that I will use information connecting with maximum height. So I will know that I need to summarize information for the y, a direction. Let me summarize it here in this case. I know that my u in the y will be 12 cos of, 12 sine of theta. We are resolving this u to the vertical. And I know that my displacement in the y in this case is 5.3 meters. Then acceleration in the y will be negative 9.8 meters per second squared. Then the velocity at that point is equal to 0. That is velocity in the y. V in the y is equal to 0 meters per second. And then lastly, the time to reach this point, we do not have it and we may not need it. So when you look at this information, you realize that if I use the third equation of motion, I can easily get my angle, because I have u, which is in the third equation of motion. I have s, I have a, and I have v. So the only thing I will be lacking will be theta. So using v squared is equal to u squared plus 2as, and considering vertical motion, I know that my velocity at the maximum height is 0 squared equal to u squared, which was our u is 12, then sine of theta, and this whole thing is squared, then minus 2 times 9.8 times h, which is 5.3. So here we'll have 0 squared equal to 144. When you square 12, you get 144 sine squared theta minus 103.88. And when we take this side, we'll have 103.88 equal to 144 sine squared of theta divided by 144 by 144. You will have sine squared of theta equal to 0.7213, and you can now take the root both sides. When you take the root both sides, you will have sine of theta equal to 0.84934. And after that, if you take sine inverse, your theta will be sine inverse of 0.84934, and finally you have your theta as 58.1 degrees. That is the angle. We have got it now. So you can see things are very easy and very simple. We are using the three equations of motion, nothing to worry about. Let's now look at question 4, which is the last question in this part. And our question 4 says, a particle is projected with a velocity of 6.2 and 29.4. So here they have given you the velocity in the x and the velocity in the y in vector form. Then find the time taken for the particle to reach its maximum height, the maximum height, the total time of flight, and the horizontal range. So in this case, this is how a particle moves, and they have given us this velocity. So here we do not need theta. So here you don't need to worry. Since they have given you u as 6.2 and 29.4, that means this is u in the x will be 6.2 meters per second, and u in the y will be 29.4 meters per second. So nothing to worry about. So here you realize that you will not need the angle theta. You don't need it. So with that information, you can go and calculate the time taken for the particle to reach its maximum height. So using the first equation of motion, which is v is equal to u plus at, and considering vertical motion with u, our u was 29.4, our a is negative 9.8, and our v at maximum height is equal to 0. So we are looking for the information for maximum height. So we know that 0, if we substitute them here, will equal to u, which is 29.4 minus 9.8, then t. So you realize that if you bring 9.8 t here, you will have 29.4. When you divide by 9.8 by 9.8, you will have your t equaling to 3 seconds. So I think you can see how simple life is. And then for part B, we want the maximum height. We want the maximum height. So for the maximum height, it is the distance here. So we are going to use now the second equation of motion. Let me erase this information here so that we can now calculate that one. So for maximum height, that is for part B, using S is equal to ut plus a half at squared. I'm considering vertical motion with u equal to 29.4, then v will be 0 at that point, and then t will be 3. So if I substitute in here, I will have my s equal to u, which is 29.4 times t, which is 3, time taken to reach maximum height, and then minus a half times 9.8 times t squared, which is 3 squared. This becomes 29.4 times 3 minus 9.8 divided by 2. You'll get 4.9 times 9. And this is our s, which is our maximum height. You'll get 44.1 meters. So you can conclude and say, therefore, the maximum height is 44.1 meters. Then, so the next thing here is the time, the total time of flight. If we have this, the time here as 3 seconds, then the time of flight will be 6 seconds. So that one we don't need to suffer with it. The next thing I'm going to calculate is the horizontal range. So for part D, I know that for horizontal range we are using information for the x direction. That is for part D. I know that r will equal to horizontal displacement of velocity, which is u, and u in the x is, we had u in the x as, u in the x is 6.2, so I will say this is 6.2, then times the time of flight, which is 6. So the range in that case will be 37.2 meters. So things are very simple here in projectiles. So here, the next part we are going to look at will be release at an angle from a given height.